to 10 for today, so conclude this stuff on microstructure, and then over the break, read chapter 11. But no one has looked at chapter 11, okay. Because I do not remember how I presented this material, and so I'm just gonna, I think I just leap in, but nonetheless, let's do it. Let's see how far I get. And what we're gonna be talking about, which I find fascinating in the last part of the class, is electronic materials. The last 5 lectures, 3, 2, yeah. The last 5 lectures, electronic materials. And it's essential to understand the electronic materials to understand the material that we're gonna do today, at least have a background on it. So let's get started. So whereas we talked about the mechanical properties of materials, we talked about defects and how energy is distributed as a result of defects. Well, now we're going to talk about a different kind of defect. Instead of defects in the arrangement of the nuclei of the atoms, we're going to talk about defects in the electrons. So we're going to talk about how electron defects. So let's take a starting point and get an idea of what we're going to be looking at. And what we're going to be thinking about, we're going to be taking as our example, not as our example, we're going to be studying silicon. So we're going to be looking at silicon. So let's start out by drawing a really simple picture of where the electrons are in silicon. And for this, we're going to rely on the Lewis model. And so silicon, we're going to, does anybody know off the top of their head how many valence electrons silicon has? 4, very good. It has 4. It's in that column. And I'm walking back and forth. You've got a big angle here. So there are 4. It's in that column. It's such a pain in the butt to be in these rooms where we have no periodic table, but it's in that column underneath carbon. And it's got 4 valence electrons. And when I use the word valence electrons, how many people go, yeah, I remember what that was talking about. Cool. You did get something out of Kim 1. So we're talking about valence electrons. And so we've got silicon here. And let's just start with an idealized model. And of course, I'm going to use, as I said, we're going to use the Lewis model like this. And so silicon has 4 valence electrons. And I come over here, and silicon it's now going to form bonds. Oh, I want it to be this way. I have a reason for this. And it's going to form bonds, and it's going to have basically something that looks like this. So each silicon is going to have 4 bonds to its nearest neighbor. Does anybody know what that local coordination is going to look like? What structure it's going to look like? Tetrahedral. What does that look like?
Like you have the 1 on top and 3 legs.
1 on top and 3 legs. Yeah, I like it the other way around. So bond, 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 tetrahedron. Anyhow, all right. I just do that because I wanted to be a cheerleader and never got to be it. Okay. So I'm going to draw these bonds now, not with 2 dots, but with this. And so we have this big crystal. In fact, it's a diamond cubic crystal. We'll come back to that later. For our purposes right now, it doesn't matter what it is. So I have something that looks like this. Okay, so every silicon atom now is surrounded by 4 others to which it's bound, and every bond now has 2 electrons. Okay, as I mentioned, what we're going to be talking about now is defects in the electron density. What happens to the electron density as a result, how these defects basically influence properties. So, here's my basic look at silicon, and what can happen here is one of these electrons, let me put a few more silicon atoms in here, okay? Of course, this is a crystal, so it goes on often ad infinitum. But let's replace 1 with a blue dot. So I want to think about that electron, which is associated with this silicon atom. And now, let's imagine that something happens. I mean, well, we'll come back to this. What can happen here, and by can happen means it's got to be thermodynamically allowed. What can happen is this electron can pop off. It can pop off here and go reside on this silicon atom.
Okay? Now, once on that silicon atom, now, this one has its 4 valence electrons around it, but 1 additional electron, so it has a total of how many? 5, and so what's the charge on this thing? Minus 1. Everybody good with that? So it's a charge of -1 on this one. There we go. And what does that must mean that the charge on this silicon atom from which that electron came? What is the charge on it? +1. All right. Now, what's really cool is when that electron gets on that one, it says, hey, I could just as easily hop over here now. So it can basically hop over here. And it basically begins to do this process that we talk about in various terms. We talk about this as a random walk, that the silicon just kind of randomly, this particular electron rather, randomly hops from silicon to silicon. So all of these silicon atoms out here are indistinguishable to this, and it just hops around. Every so often it may come back here and hop back onto this one, but these out here just hops around in general. So it basically moves around. We call this a random walk. It's also called a drunken man's walk. Okay? The idea of you getting drunk, you just kind of stagger around with no particular direction in mind. Everybody good with that? Okay, so this electron can move around. Now, if we want to describe that process, I'm asking you, what do we need to know? So we started out here with this thing in a particular, this electron in a particular, I'll use a buzzword here, energy state. All right? When this electron hopped over here, what's the buzzword I want to use now? It was in a particular, oh, good. What is it?
Change in energy state?
Changed its energy. So it went from some value here, this electron now, so it went from some initial energy value, and it hopped up here and it went to some final energy value in this process. And then it hops from site to site to site. Does it change its energy value when it hops from site to site to site? No, I like that. So now you say no. Why is it no?
Because he said no and you said you would.
Because this one, the silicon over here is no different from the silicon over here. The only place where it changes is in close to here. Are you good with that? So now it hops around. Okay, now, give me a whole bunch of terms, a whole bunch of things we would want to know to describe this scientifically. So Elizabeth, tell me what we want to know to describe this scientifically. Let's think back to how we described things before. What is that EI minus EF? It'd be conservation energy, so we've got to conserve energy, so somehow we put energy into this thing to get it to go there. And then, let's do it this way. How many electrons are moving around in that material? So, this one could be, I basically excited this one from here up to there. I changed its energy. Could it happen over here?
Yeah.
Could it happen here? Could it happen way over here? What do I need to know to talk about how many there are? Or, anybody want to take a shot?
Total energy?
How many? If I had some number to begin with, and I have some number that are hopping around, I might want to ask about what? The probability! What an amazing term! What was wrong with the way you said that?
Well, probably, it's not exactly.
No. You said the probability?
Oh, I was asking a question.
That's right!
You want me to read words like
You know this material, it's the probability. Okay, let's get somebody else now. If it's the probability, there must be some equation that drives that. What would that equation be? Not the actual equation, just the name of the equation.
Boltzmann.
That's all I got, 2 people. Boltzmann. So we've got the Boltzmann distribution. So the Boltzmann distribution now, to get at that, I need something. What do I need to know? I need to know something like this. So let's write down the Boltzmann distribution. distribution. So if I wanted to say the probability of having an excited electron, so the probability of having a moving electron, we call it. So moving electron, that's me. It's also my initials, Mark Eberhart. Great initials, right? Probability of having a moving electron now goes as some constant A, e to the minus delta E over K B E. Right? All right. What's this delta E? Where is it up here?
Energy from the final energy minus the initial.
Oh my God, it's the energy from the... All I have to know is something about the initial energy state and the final energy state. Okay, so what we're going to do now is we're going to think about that. Now, I'm going to give you the answer before I start. So, what we know is each one of those electrons up there. This is what we call band theory, or the band model, let's call it that way, band model. And by band, I do not mean a group of instruments, playing a group of instruments. I mean something quite different. Now, so what I'm going to do is I'm going to give you the kind of the answer, and we'll describe this, and we probably will not have time to come back and actually get at the science behind how these bands are determined. But that's fine. Anybody who's interested in it, I can give you reading. You can come see me. And I may have written about this in the book. I just don't remember. Okay, now, what this is, the band model tells us about the allowed energy levels for electrons. Okay? So the allowed energy levels for electrons. The band model is the energy of electrons. And electrons are very curious creatures. That is, they do not like to have the same energy as everybody else. They like to have a different energy than everybody else. What this means is that no two electrons within this very simplified model I'm giving you, no two electrons in this band model. That's not right. For the sake of what I'm telling you here, and you've already done this, right? For the sake of what I'm telling you here is electrons only like to have one partner who has the same energy as they have, so they form this partner. So no so pairs of electrons, so no two pairs of electrons. I'll say it this way, can be in the same energy state. Now, somebody tell me what that's reminding you of. What did you learn in chem? Well, yes. Spin. And so when we were talking about this, spin came into play where? I mean, you guys talked about s orbitals. Is that a yes?
Yes.
And p orbitals?
Yes.
And g orbitals and f orbitals? Did you actually talk about f orbitals? Did you draw pictures of f orbitals?
No.
Did you draw pictures of p orbitals?
Yes, we did.
I
We
think
have
we
like
did. It was more like
we
we
had
recognized
SPB
it.
orbitals that we drew out.
Okay. Okay. So individual atoms, you already have this knowledge about. So let's do silicon. So an individual silicon atom, it has this 1s state, this core state down here. And it's called 1s. All right? And then the next step up, we have this set of orbitals, these 2s and 2p orbitals. That would be carbon, actually. Now we go up a little bit higher, and we have 3s and 3p orbitals. Okay. And now we fill these up. And for silicon, we fill these up, and we put how many electrons in each state?
One. And then you like come back and do two.
They're flipped
Oh, let's just start putting electrons in. Okay, we're just putting electrons in. We put one in and spin up, and one in and spin down. We just try to start filling these things up. And I'm not going to worry about the exact filling because it's going to make no difference when we go a little bit further. And now we get up here to silicon, and when we get up to silicon, we'll put them all in like this for the hell of it. So we've got 4 electrons, and they all go and spin up. Now I can't help it, since we'll do something special since you guys are the only ones here today. What do you picture? This is totally beside the point. What do you picture when you think of a spinning electron? Spinning? Yeah, and you know how good a model that is?
Really horrible.
Oh, it sucks. It's one of the worst models. So, I'm going to tell you something. Again, this is totally unrelated to this, but it is so cool. I got to share this with you. So, what happens when when we rotate an electron through 360 degrees? Here's the cool thing. When you rotate an electron through 360 degrees, that should be a symmetry element, shouldn't it? It should come back, and it should be exactly where it was, so you couldn't distinguish it. That's not what happens. You know how many times you have to rotate an electron around before it comes back where you can't distinguish it? You have to rotate it around 720 degrees. You have to rotate it around twice before you can't distinguish it. Now, you go, that's crazy. But I'll show you an example. Okay, so this is an electron. It's got spin down. All right? Now, let me rotate it through 360 degrees. Now, if I was a ballet dancer, which is a Thailand form of dancing, this would be really cool. I've seen them do it where they have where they have a champagne glass here and they do this. I can't do that. But here we go. I'm going to rotate it through 360 degrees. Spin up. Now I'm going to rotate it through 360. Oh, it's spin down. I had to rotate it through 720 degrees to bring it back on itself. Is that cool or what? That's what an electron is. That's what an electron is. So spin tells you have to, if it has spin 1/2, it means I have to rotate it through 720 degrees to bring it back on itself. That's what spin is. It has nothing to do with an electron of charge spinning around like a basketball. Now, it blows my mind that they take this amazingly incredible, interesting thing and turn it into something stupid. Go ahead.
I was just kind of wondering, like, where you're measuring that 360 degrees.
So watch my fingers. Okay, so here comes. Okay, so can I do it through 360 degrees? Oh, I should have brought my spinner. You can also, this is a real thing too. You can also take 2 things and you can tangle them up. So you can take things that are connected by threads and you can rotate it by 360 degrees and there's nothing you can do to untangle it. Then you rotate it by 720 degrees and you can untangle it. Oh, this is so cool. I'll post it. Okay. Oh, shoot, we're just... Anyhow, so we have these states. Now, when we put things together, the band model, we put a whole bunch of atoms together into one place. So in a crystal, this is for an isolated atom, we get these bands. So let me draw a picture of what these look like. Now, these are states, and I'll do it for silicon. These are states. And what I have here is energy states that are so tightly packed. So the energy between these states is so close together. So each one of these lines represents like one of these lines over here. Everybody okay with that? So I've got these things so closely packed together. I've got something that looks like this. And then suddenly, I have now another one up here, which is tightly packed together. All of these states are tightly packed together like this. All right? And in this region here, the electrons have no region, okay? They have nothing to be. So I have these states. Now, just like over here, and when I say these things are tightly packed together, I mean they are tightly packed together. They are this teeny, 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 teeny fraction. And we'll come back and see if we can get to that. They're this teeny, teeny fraction of an electron volt. We'll talk about that in a minute. Is 10 to the minus 26 joules between each one of these. Maybe more than that. Maybe more like 10 to the minus 40th joules between each one of these. The energy spacing between each one of these is very, very small. Okay, so what are we going to call these? We're going to call these bands. So there's one band, and we can give it a name. In this particular case, we would call this the valence band. And here we've got a band. And so we've got these bands of energy where electrons can be. They can have energy. So we've got these bands of energy. Now, the electrons, these are just like those over there. These are like orbitals, like 2s, 2p. These are not, do not picture these as electrons. Picture these as what they are, available energies for electrons. Now we can come and we can start putting electrons into these bands. As we put electrons into these bands, we want to recognize two different possibilities. All right? So we're going to want to recognize two different possibilities. One possibility is where we put electrons into these bands and they don't fill the bands. So of these possibilities, unfilled bands and that would be a picture like this. All right? What's the other possibility? If I'm designating unfilled bands, what's another possibility?
Filled bands.
Filled bands. So another possibility is filled bands. So I put electrons into these things. I've got filled bands, I've got unfilled bands. And of course, if I want to draw the picture of the filled bands, what would I need to do here? Fill it all up. Okay, now, what we're going to find out is unfilled bands give rise to a particular property. What property might that be? I'll tell you, metals, most pure metals, have unfilled bands.
Conductivity.
Oh, what did you say?
Conductivity.
Conductivity. What we'll realize is unfilled bands give rise to things that are conductors. And filled bands give rise to things that are insulators. Yes, sir.
Just point of clarification, is a full grouping of the bands like considered a band, the grouping of the energy states, or is each individual energy state a separate band?
No. They're so close together we can't distinguish them. We can't even see any energy. We can't distinguish the energy between them. So we call that whole collection a band. Okay?
That's what I thought. I just wanted to make sure.
And in fact, as we go on, we would call this one here, in this picture, we would call this one the SP band. So we know it's made up of, on the individual atoms, S and P, where it goes through the individual atoms, okay? So we're going to talk about unfilled bands and filled bands, and understand why do unfilled bands give rise to conductors, and filled bands give rise to insulators. That's not a question. We're going to figure that out, unless anybody knows. Yes?
It's easier for the electrons to move.
You're just telling me you do know. Cool. So let's look at this. Let's look at this. We want to now describe these bands and talk about what's going on in these systems. So first of all, we're going to be dealing with an interesting unit. So our unit of energy, that's what we want to get to for our Boltzmann equation. Our unit of energy is going to be the electron volt. Okay? Now the way I want you to think about this is a volt is like we could have defined energy in terms of how far a weight dropped. Is everybody with me? We could have gone back and said, hey, we're going to define a unit of energy for when 1 kilogram of mass falls through 1 meter. We could have done that, couldn't we? Okay, now in terms of electrons, What they're falling through a electrostatic potential. They're falling through an electric potential as they fall. So we define a unit as the charge on an electron falling through a potential of 1 volt. Okay? That's a very handy unit. It's a very handy unit to describe things in. And we're going to want to talk, and it's just an energy unit, but think about it as how far an electron falls or rises in order to change its energy, just like moving a mass in a gravitational field. And this is equal to 1.6 times 10 to the minus. I wrote this down somewhere here.
Just a second.
1.6 times 2.
It's negative 19.
I got it right.
You got it
Yeah,
right.
you got it right.
1.6 times 10 to the minus 19 joules. So it's this incredibly small amount of energy. Now, what we want to do is figure out how many particular bands there are, how many electrons a band can hold. Okay? That's where we're going to start. We're going to figure out how many electrons a band can hold. So let's do that. And we're going to start out by saying how many possible states are there in some crystal. Okay? Some great big huge crystal. The first thing we want to know is, so if we're going to talk about silicon, every silicon atom will bring with it 4 different places where an electron can reside. Okay? Which are just the s and p orbitals we talked about. So 4 different places. And you're nodding because you really understand here. Cool, I love that. Because your eyebrows are unexpressive. Oh, it's not your fault. That's cool. Okay, so silicon has, each one brings with it 4 places where an electron can be. So 4 places where an electron can be. It also brings with it what?
4 valence electrons.
It brings with it 4 electrons. Okay, it has 4 places. And how many electrons can each place hold? 2. Again, say that like you mean it.
It holds 2 electrons.
Absolutely. So each one can hold 2 electrons. Cool. All right. So let's figure out how many places there are in a how many bands. What's the word I want? Let's figure out how many places there are in a particular band. All right. Now it would seem easy, but first thing we need to do is say silicon is a diamond cubic structure. Okay? Now we talked about this before. A diamond cubic structure, we talked about it in passing, is basically an FCC lattice. An FCC lattice with how many atom bases?
2.
2? Is everybody good with that? With 2. That means in every unit cell, primitive unit cell, there must be 2 silicon atoms per unit cell. Okay. Now, we can now distinguish this. Damn. We don't have nearly enough time. We can now distinguish this when we bring these things together. There are 2 possibilities for how to put those valence orbitals together. Now, somebody remind me, if I have 2 silicon atoms per unit cell, all right? I have 2 silicon atoms per unit cell, and I can now put electrons in here. I can put electrons into this region. If I put electrons in here, what region am I putting it into? This region here. Yes!
The binding.
Cool! You were so excited about that. Okay, cool. So this is the binding region. And out here it's the
Anti-binding.
anti-binding region. Okay, when I bring these two silicon atoms together, to form a unit cell now, I'm going to bring their places together, and I'm going to get my places are going to now look different. So I'm going to get 4 places, 1, 2, 3, 4, that correspond to putting electron density in the binding region. All right? So imagine I'm bringing these places together, and in one case I bring them together, and they go, oh, we can put all of the electron density in the binding region. All right? Where do you suppose, and it's also going to form 4 states. And now in this particular case, what do you suppose it's going to look like? Where's the electron density going to go? It formed 4 that sits in the binding region and 4 that sit in the
Anti-binding.
anti-binding region. Cool. So I'm going to get something that looks like this. All right? Now, let's imagine I take these 2 atoms. All right? Those are my unit cell. And now I'm going to build up a crystal. And I'm going to bring them together. And I'm going to bring that 2 orbitals together with 2 more. That set of atoms together with 2 more. You good with that? Can you imagine that? All right. So let's kind of draw a picture of that. So I've got 2 here. There's 1 unit cell, and now I'm bringing together with 2 over here. All right. Now the cool thing that happens is this set of 4 orbitals, this set of 4 binding orbitals, and this set of 4 binding orbitals, they don't have exactly the same energy. I get another set of 4 that are just a little bit different in energy than the isolated atom, the isolated pair of atoms. Are you guys with me?
No.
Who's not with me? Explain what you're missing.
I'm not sure which set of 4 is which, and like, are you trying to, is there significance that they're on top of each other? Like, is that energy going up or down?
Yes.
Or something like
So
that?
energy is going up this way. This is energy. And I took my 2 atoms, I'm thinking of assembling my crystal together. So I took my orbitals from 2 atoms, and now I bring 2 more atoms together, and I assemble them right there. Okay? And now I've got a total of 8 places, binding places to put electrons, and 8 anti-binding places to put electrons. Okay?
So which are which in that case?
So which ones are the binding electrons?
The lower ones.
The lower ones are the binding electrons. And which ones, are you with me? And these are the anti-binding electrons. So these are the anti-binding.
Is this to be potential energy, or is it just energy?
This is potential.
That's what I thought. Okay.
That's potential.
Yep.
Now these are places to put the electrons. Okay? All right, so these are places to put the electrons in a binding and anti-binding place to put the electrons. Okay, so now let's imagine we do the following. Let's imagine we put, now we assemble 4. We bring 4 of these things together. So 4 unit cells. Okay? You with me?
So now we have 16.
You tell me what this would look like. What would happen when I brought 4 cells together?
Maybe 16 is a binding, wouldn't there?
I've got 8 here. How many people think I get 16 here? 1, 2, 3, 4, 5, 6, 7, 8. So 8 from those and 8 from those.
Yeah, that makes sense.
Okay?
I think there might be more.
No, there can't be more. Each atom only brings with it 4. So if each atom brings with it 4, and I've got, so each one brings with it 4, then I must now have something that looks like, all right? you with me? And these are the energies of those. How about this one? Same thing. Cool. And will these have exactly the same energy as these? No, they won't have exactly the same energy. They'll have a different amount of energy. Okay. So here's one. Let's imagine that we keep doing that process now, and we have now a total of N cells. Okay, we've got a total of N cells. How many states am I going to have down here in the binding region if I have N cells? Is that correct?
What are we
So
defining?
this is 1, 2, 3, 4.
Then yeah, 4.
So there's going to be 4 N down here.
Yes, I think so.
Cool. 4
I'm like, wait a minute.
There'll be 4 N states when I get there. And what size a number is in?
However big or small you want it.
Yeah, but if I'm talking about crystal, how big is that?
Really big.
Really big. It's a lot.
It's a lot.
And how many in the anti-binding band?
4N.
4. Now, and what we'll discover is that the anti-binding band and the binding band are now separated in energy by what's called an energy gap. Okay? You good with that? Really neat. So it's separated by an energy gap. Now, let's put electrons into this. Each one of these can hold how many electrons? Each one can hold 2. So the total capacity here is how many electrons?
8N.
2 times 4n. Right? 8 electrons. So 8 in electrons can be held there.
Same thing for the top one.
And 8 in electrons can be held here. Cool. Now, how many electrons does each silicon atom bring into this situation? 4. So, if I have N cells, how many atoms do I have? N cells, how many atoms per unit cell, per primitive unit cell? 2. So if I have N cells, how many electrons do I have?
8N.
I have 8 N electrons in the crystal. Oh, wow. And this band can hold how many?
Wait. If you have N cells, you have 8. Wouldn't it be 16? Because you have 8 in the binding and 8 in the anti-binding.
It's not filling all the bands.
So we're going to put electrons into it now. You've got me questioning myself. We're going to be putting electrons into it. Each silicon atom brings how many?
8.
8. How many silicon atoms per cell?
2.
Pardon me?
Oh, it brings 4. Okay.
Oh,
Yep.
I didn't jump all over you
Yeah.
because you're always right.
Not true.
So it brings how many electrons? That brings how many electrons?
Each
Each one
cell
brings
is 8.
4 electrons.
So
So
the cell
2
brings
per
8.
cell
Yep.
is 8 electrons per cell.
Yep.
And now I've got how many cells in? So I've got 8 in electrons.
Yep, I'm good now.
So when I get to silicon, it'll do what? Will it fill up this band?
Oh, just that one?
Just this one?
Oh, yes.
Yes! Yes!
Talking about the
Oh,
actual-
you're questioning now. Tell me what you're confused about.
Get all the numbers confused. All these 2.
Okay, let's back up and make sure this is clear. So, the number of states each cell is going to bring together, each cell is going to bring together 4 states, 4 places to put electrons in the binding region, and 4 places to bring electrons in the anti-binding region. Okay? That's in each cell. Now, each one of those can hold how many electrons? 2. So the total number of electrons this band can hold is 8 n electrons. All right? Now, we're going to bring those together. We're going to put the electrons from silicon into these places. All right. Now, each silicon atom has 4 valence electrons, but there are 2 silicon atoms per cell. Right? So that means there are 8 electrons per cell. And we're going to put those in there, and we have n cells. We'll just fill up this band. You good with that?
Or you can just fill up the antibody.
You can just fill up this band here. So we're going to fill this up. And now, if I want to move an electron from the binding band to the anti-binding band, I have to put how much energy in. This, by the way, is this energy gap is denoted E sub G. So how much energy do I have to put in to move it up there?
E sub G.
E sub G. I have to put E sub G in. Okay, cool. We're doing all right. There's a much more elegant way to build this, but that's okay. This will work. All right, now, let's do the following. Let's do the same thing, but let's imagine this is the case for the diamond cubic lattice. Let's do the FCC lattice. Yes?
So how do we know that the lower energy band corresponds to the binding?
Because it's the lower potential energy state.
Because it's the same. How do we know this? Well, if I look at what we talked about, when we talked about the binding region, okay? We talked about the binding region. Those electrons sitting between the atoms, are they at a lower potential because they see both nuclei?
Yes.
That's how we know that it's at a lower potential. They go to a higher potential. Now, that's kind of a cop-out. The actual way we know this is by solving the equations of quantum mechanics and actually determining this energy. But we're not going to do that in this class, okay? And we also can verify this experimentally. We can also do this experimentally and verify this, all right? Now, what's interesting is, no, I won't go into that. Okay, so we're there, we've got 5 minutes. Now, let's do the same thing, but let's imagine that we brought together the same number of atoms, but we formed an FCC cell. In this case, how many electrons are there per? How many atoms per primitive unit cell in FCC?
Oh, primitive.
Per primitive cell.
Primitive 1.
1. Are you good with that? There's 1. Okay,
Pulled a
cool.
sneaky on me.
So there's 1 atom per cell. Now each atom, so let's put this together. Let's put all these things together. Now we're going to build these things. So let's build our binding band. So when we build our binding band now, we're going to have, for our binding band, we're going to have, oh, there is no anti-binding band. Bear with me a second while I think. Okay. Oh, no, this works just fine. So we're gonna build this up, and we're gonna build up our binding and anti-binding. So what we're gonna do is we're gonna discover, we're just gonna build these up. There is no anti-binding combination, right? I've got 1 atom, there's no anti-binding combination, is there? Right. So let's just do this, and we're gonna start building this thing up. And now we bring we bring our cells together, and we get for n cells, we get for 1 atom, we get 4 states. Right? And for 2 cells, we get how many states?
8.
8. And why is there no anti-binding state?
Because each one is a single atom.
Each one's a single atom. So we're going to go on and do this, and we're going to bring this up, and we're going to bring together n cells to make our crystal. And when we bring together N cells to make our crystal, how many states will we have? 4N. Now, each one of these atoms brings how many electrons? 4. So each one brings 4 electrons. So this will hold a total of how many electrons? I'm sorry, this will hold a total of how many electrons? Let's do that first.
8.
Oh, wait.
8 in?
Oh, it holds 8.
8 in?
I keep getting tripped up by that.
And each one brings how many electrons?
4N.
4 in. So, when I put 4 in into 8 in states, how full is this band going to be? Half full.
We'll never get higher than that.
Whoa, this is so cool.
Except this is
Let's take a quick look. So if we look down that column, let's look down the column. So we're going to do carbon, silicon, germanium, tin, lead. This is our column. All right, now let's do the following. The structure of carbon is what? Diamond cubic. That's where it gets its name. So that structure gives rise to what mineral?
Diamond.
A diamond. How many people have seen a diamond? Everybody's seen a diamond, right? So this is diamond cubic, which has how many atoms per unit cell? 2. Silicon is diamond cubic as well.
So it also has 2.
Germanium is
I got no clue.
FCC?
FCC?
diamond cubic.
Diamond cube.
Now tin, we looked at tin, but we talked about it as being body-centered tetragonal, which it is at room temperature and above, but below room temperature, well below room temperature, guess what?
You got FCC? Yeah.
And we talked about lead, and it's what?
It's
FCC.
FCC.
So what's
What can you tell me about that? Is it a conductor or not?
their conductor?
Oh, is lead a conductor? Don't go for it.
Tin and
It's a
lead are
conductor.
both used in solder.
This,
They're definitely
this is a
conductors.
metal,
They better be.
and these
Not so much. Semiconductor?
are called semiconductors, but for the purpose of our discussion now, they're insulators. We'll come back later and talk about what makes them semiconductors. So what we've done, and before you leave, what we've done now is these are diamond cubic, and because they're diamond cubic and they have this number of electrons, they have what property?
They're semiconductors.
Insulators.
They're insulators.
They're not.
And these, because they have this structure, they are
Conductors.
conductors. This is an example of what kind of a something property relationship.
Structure property.
Okay. Who's going someplace cool? Who's going someplace cool? Anybody?
I'm going to Pittsburgh.
Pittsburgh. That's cool. Anybody going someplace else? Anybody leaving Colorado? Yes, where are you going? Wow, what part? Ooh, is it nice there? Wow, where are you going?
Albuquerque.
Albuquerque. Always nice in Albuquerque. You guys have a very nice time. We will see you in a week.
Only one